Most engineers have used this equation at some point. Tau equals TR divided by J. It's one of the first torsion formulas we learn in mechanics of materials. And because it works so well in textbooks, many people assume it works for every shaft. But here's the catch. This equation is not a universal torsion formula. It was derived specifically for solid circular shafts. Apply it to a square or rectangular shaft, and the results can be seriously misleading. In this video, we'll put that assumption to the test. We'll compare analytical calculations with ANSYS simulations and discover why this famous equation works perfectly for circular shafts, but fails for non-circular ones. Let's compare three solid shafts: a circular shaft, a square shaft, and a rectangular shaft. All three are made of the same material, have the same length, and are subjected to the exact same torque. The only thing changing is the cross-sectional shape. For the circular shaft, the classical equation predicts a maximum shear stress of 50.9 megapascals. ANSYS predicts 51.2 megapascals. The angle of twist is also almost identical. The error is less than 1%, which is excellent. Now look at the square shaft. The analytical equation predicts only 29.9 megapascals, while the simulation shows 48.6 megapascals. That's an error of more than 60%. The predicted angle of twist is also much lower than the simulation. The rectangular shaft performs even worse. The equation predicts only 12 megapascals, but the simulation gives 20.4 megapascals. That's nearly a 70% difference. So why does changing only the shape create such a huge error? The answer lies in how different cross-sections deform during twisting. A circular shaft has perfect rotational symmetry. Every point on its outer surface is the same distance from the center, so the entire cross-section rotates together and remains perfectly flat. Because the cross-section stays flat, the shear stress increases smoothly from the center to the outer surface and remains uniform around the circumference. These are exactly the assumptions used to derive the classical torsion equation. A square or rectangular shaft behaves very differently. As it twists, the cross-section no longer stays flat. Instead, it warps, meaning different regions deform by different amounts. This completely changes how the stresses are distributed. The corners experience very little shear stress, while the maximum stress shifts toward the middle of the longer edges. Since the original assumptions are no longer valid, the classical equation can no longer predict the correct stresses or angle of twist. To accurately analyze non-circular shafts, engineers use St. Venant's torsion theory. Unlike the classical approach, this theory accounts for cross-sectional warping and the resulting non-uniform stress distribution. Instead of relying only on the polar moment of inertia, St. Venant introduced correction factors that depend on the shape of the cross-section. These factors capture how different geometries resist twisting. When we apply St. Venant's equations to the square shaft, the predicted maximum stress is 48.1 megapascals, while ANSYS gives 48.6 megapascals. The angle of twist also matches almost perfectly. For the rectangular shaft, the agreement is even better. The analytical solution predicts 20.3 megapascals, and ANSYS predicts 20.4 megapascals. Once warping is included, theory and simulation agree remarkably well. So what should you remember? The equation tau equals TR divided by J is correct, but only for solid circular shafts. Its accuracy depends entirely on the assumptions used during its derivation. If you apply the same equation to square or rectangular shafts, it can significantly underestimate both the maximum shear stress and the angle of twist. That can lead to unsafe designs or incorrect engineering decisions. For non-circular shafts, use St. Venant's torsion theory, publish torsion constants, or finite element analysis. These methods correctly account for cross-sectional warping and provide accurate results. One final note: everything discussed in this video applies only to solid shafts. Hollow shafts behave differently under torsion, and their analysis deserves a separate discussion. We'll cover that in the next video, so stay tuned. If this helped you become a better engineer, subscribe to the STEM Forge for more practical engineering insights.